Okay, hi everyone, it's me, and I'm just going to work out a few select answers here from the homework that you did. And I tried to pick some of the more juicy ones, and I also tried to vary those that I picked. Okay, so number 77 first. This question is, it says, consider the function f of x, y if you start at the point 4 comma 5, move toward, okay? So a couple of things that you want to just be mindful of here, and it's all about just being clear, conveying clearly what it is that what you're doing. So if you're starting at 4 comma 5 and you're moving to 5 6, what you're implying here is that your vector then is going to be the vector 1 1, which is not unitized or normalized, so I'm going to normalize it. Okay, and the fact that you're told in the story that the directional derivative, if you move in this direction, is 2, what that is saying is that the directional derivative in the direction of vector u of the function f at the point 4 5, this equals 2. Okay, and then there's another scenario. You're told that if you're at 4 5 and you go to the point 6 6. Okay, well then this vector is going to be, let's see, what is it? This vector is 2 comma 1, right? And let's just quickly unitize it. Unitizing it will give you radical 5. 2 radical over radical 5 comma 1 over radical 5. Okay, now I'm going to be very good about being clear here. I have v and u and u. That could be a little bit confusing. So I'm going to do subscripts. So this is u sub 1. Okay, so then now what this tells you in the story, that if you move in this direction, the directional derivative is 3. So this tells you that the directional derivative in the direction of vector u2 of the function f at the point is 3. Okay, and then it asks you, what is the gradient? So what is del f? Well, what's really nice about this question, and these questions in general, as you hopefully are appreciating, it's the variety of these questions, of any questions in a math course, assuming that the math course is a richly conceptual one, is the variety is literally endless. Okay, like this one is not one that we did in class per se, right? That's a kind of a famous quote that students say, like, we never did one just like that. Well, it'd be impossible to do every question that involves directional derivatives, but if your goal is understanding, then it's easy peasy. All right, well, a couple things. I'm going to go back. I have to find this value, and I'm going to make a couple notes to myself. I know that if this directional derivative is 2, I know that is gotten by del f at 4 comma 5 dotted with the vector u1, because that's what we derived. So I know this is true. We derived that really nice generalization about the gradient's relationship with the directional derivative. Likewise, I know that this value of 3 is the result of del f at 4 comma 5 dotted with vector u2. Okay, so then if I want to find del f at 4 comma 5, I can just set up a system of equations and solve for del f. All right, so what does that mean? Okay, well, let's see. This is saying the same thing as 2 equals, I'll just call this, let's call this a comma b as my components of del f. And you know, of course, that a is f sub x and b is f sub y. All right, dotted with 1 over radical 2 comma 1 over radical 2. And this is the same thing as 3 equals a b dotted with 2 over radical 5 comma 1 over radical 5. And all we're going to do is solve for a and b. And that is easy because you know that applying the dot product gives us that equation. Applying the dot product here gives us this equation. Okay, and then all you do, boys and girls, is just solve this system of equations to solve for a and b. And once you've solved for a and b, you will have found del f at 4 comma 5. Okay, that algebra I do trust you can do on your own. All right, 80. What does 80 say? Oh, 80 is the moose question that Spencer and Oliver requested, even though it was assigned already. Okay, it says the temperature H in degrees Fahrenheit, Y miles north of the Canadian border, T hours after midnight is given by H is blah, blah, blah. All right, so the first thing I'm going to do is write down the H function, and I'm going to ask you a question. Hang on a second. Minus 5T, okay. All right, so first of all, boys and girls, if I were going to write the this H function using function notation, would it be appropriate to write, say, H is a function of y comma t, or should I write H as a function of t comma y? One of these is the better choice, believe it or not, and it is this one. The reason why is because in the question, if y, the variable y, is standing for is representing the number of miles north, it's going to be much more convenient for you to kind of label then the y component as y, since the y component by definition, you know, if you have t comma y, this is the t-axis, which is the x-axis, and y is the vertical axis y. Now, you can use this. You're just going to have to make a mental note that the distance north, y, is going to correspond to the distance right on the quote-unquote x-axis, okay? So there is one way of writing this H function that is going to be much more convenient just in terms of bookkeeping, okay? That way you don't have to kind of make that mental note when you go ahead and do the math later on. Okay, what's going on now? A moose runs north at a speed of 20 miles per hour. At what rate does the moose perceive the temperature to be changing? Interesting. Okay. Well, I guess I want you to think about a couple of things. I'm going to find something here, and I'm going to find the gradient. Now, when I find the gradient vector, and okay, hold on a second. Let me just do that. If I find del H, oh, I just sneezed before I started this pencast, and there's like little dribbles of like sneeze spray on the screen, and I hope you don't see it because it's like a splatter right about here. Okay, del F is going to equal -5, comma, -0.05. Okay, but the moose is charging, it says north. So there's a couple of things that I want to ask you. If the moose is going north, I then want to find the rate of change of temperature, which is H, by the way, right? If the moose is charging north, and ultimately the question is going to ask me about the moose's perception of the temperature change, I want to find a directional derivative, but in what direction do I want to find the rate of change of temperature? Yes, in this direction, due north. So the vector u here is going to be a unit vector that points due north, 0, 1, okay? Now I'm going to do this, and I'm going to ask you to answer a question. If I calculate this, and of course I know this is going to be the directional derivative in the direction of 0, 1, of the H function. Oh, interesting. They didn't give me a specified point, did they? So I'm guessing it's going to be either a constant value or somehow it's not going to depend, like this slope per se should not depend on the location of the moose. But I guess my question is, when you calculate this, what is this number going to represent? And what are the units of that number? You can pause me here and then do that or think about it or just keep replaying me. Well, let's see. When I dot del H with U, I get -0.05. This here tells me the rate of change, the instantaneous rate of change of temperature as a function of the distance I travel in the direction of vector u, right? That's the whole point of directional derivatives, is to find, come on, you can come on in, Ms. Cooper. Hi, Miss Cooper.
Hi.
Say hi to my calculus class. Happy New Year.
Happy New Year. I think you sent me an email that you didn't mean to send to me, so I replied to you just so you could send it to whoever it needs to go to about the bus ride home.
Whoops. That was supposed to be Kristen Fisher. That's so funny.
Well, I just figured you might need to let her know. So
Thank you. Sure. So this is the rate of change of temperature, right? So the rate of change in degrees Celsius as a function of the distance you travel in this direction of vector u. So the units of this is going to be degrees Fahrenheit or Celsius, degrees Fahrenheit per mile. Okay, so the temperature will be dropping at a rate of negative 0.05 degrees Fahrenheit for every mile this poor moose travels in this direction, which is due north. But the moose runs at a speed of 20 miles per hour. This moose runs at a speed of 20 miles per hour. So I think you can then figure out what is the perceived temperature rate of change and what are the units. Go ahead and do that as I'm finishing my masterpiece. Beard, 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 beard. Bangs, 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 bangs. Little ears, little ears. Okay, well, if the moose is running at 20 miles per hour and the temperature is dropping at this number, degrees Fahrenheit per mile, when you multiply these two, a little stoichiometry, which is the fancy word of just saying unit conversion, what you get is negative 1 degrees Fahrenheit for every hour. So this poor moose is perceiving temperature to be changing at a rate of negative 1 degrees Fahrenheit for every hour that he runs. Yay! All right, 82. Sorry, I had a little bit of a diversion. Like I said, we're all kind of getting used to just being back in the swing of things, and I too feel a little bit silly. 82, or 81, I forgot what it was. Did I say 81? 81 and 82 are so very similar. That's why I only picked, 81, okay. What does 81 say? Let's look together, shall we? 81 says, at a certain point on a heated plate. Oh, I should also say this, boys and girls, look. What's interesting is when we found, what was I saying? Oh, when we found this directional derivative or the gradient in general, you'll notice that this directional derivative and this gradient, this gradient, it didn't depend on the location of the moose or the time, right? Location or time, which gives you the sense that there is a constant direction, right? So in this context, in this problem, the direction in which there is max rate of change never changes, no matter where you are on the coordinate plane t, y. Okay, that's my point. I got distracted by my moose. 81. At a certain point on a heated plate, the greatest rate of temperature increase is towards the northeast. I'm going to stop right there. It says the greatest rate of temperature increase is toward the northeast. That sentence gives you so much information. That tells you the magnitude of del F equals 5. And del F, the actual vector, is towards the northeast, which is 1 over root 2, comma, 1 over root 2. That's del F. All right. If an object at this point moves directly north, at what rate is the temperature increasing? Okay, that question is asking you to do this. Find the directional derivative of whatever this function is f. Oh, at any point. It doesn't tell you a starting point. So again, we're looking at a possible case where the location of the point does not matter. If an object at this point moves directly north, in the direction of what's directly north, everyone? Yes, 0, 1. That's what it's asking for right here. And this, as you know, is equal to del F dot the unit vector 0, 1, which equals 1 over root 2, comma 1 over root 2, dotted with 0, comma 1, which then equals, at the end of the day, 1 over root 2. See how these questions kind of embed the idea of the directional derivative and the gradient within the question, just in different contexts. Okay, what one's next did I say? 95, is that right? Did I say that? 95. Okay, like I tried to pick a variety. Okay, 95 was a wonderful question. 95 says, are the statements true or false? 95 is false, and let's make sure we know why. Because for true or false questions, it's important that you not only get the answer correct, but that you know why. Okay, so it says, if the point AB is on the contour of some surface set equal to a constant. Okay, let's just set that up. So let's say that, I don't know, let's say there's like some, that is the contour or level curve when z equals k. And there is some point a comma b on it, okay? It says that the slope of the line tangent to this contour must be, okay, f sub y a comma b over f sub x a comma b. One of the issues I have with true-false questions that are written in many texts, including this one, is that that verb is should be must. Because there are cases where this situation could be true, but is it a must situation? The answer is no. Anyway, does the slope of this line, must the slope of this line equal this entity? F sub y at a comma b over f sub x at a comma b? The answer is no. This is a false statement, because here's why. The slope of this line is independent of these partial derivatives, and these partial derivatives depend on the value of other level curves around this curve, z equals k. So let me give you some examples. Let's say, for example, there were other level curves, and maybe this is, I'll just give you one example. Maybe z equals k for all of these. Like maybe we have a surface where z equals 7, z equals 7, z equals 7. In other words, our surface is quote unquote flat, right? Okay. If this were the case, what would f sub y at AB be, and what would f sub x at AB be? Well, these would both be 0, right? And clearly the slope of this tangent line is negative. Okay, so again, the reason why this statement is a universally false statement is because the slope of a tangent line is completely independent of these partial derivative values. And these partial derivative values depend on the values of z at other level curves within the vicinity of the point a comma b. Okay, was that it? Oh, there's one more. I think 101. 101, true or false? Okay, this one should be quick and dirty. The directional derivative is parallel to u. I hope that you saw this and almost spat with disgust. Of course this is false, for heaven's sake. This is a scalar quantity. This is just a number. This is a vector. What on earth? How could a number be parallel to a vector? Such nonsensical questions. Okay, so I hope you spat in disgust. All right, you were an absolute pleasure to see this morning. I really enjoyed our class. I really enjoy our class generally. Max, thank you for the anecdote. For those of you who didn't hear, Max shared with me at the end of class that when he went to a college visit, I think it was it Kenyon, Max, or was it Williams? I don't remember. Anyway, at one of them, he said that at that class, they were learning this exact lesson, the lesson we had today on the gradient and the, geometric relationship between the gradient and the level curves. And I said, really? Was it a good class? And he said, yeah, it was a very well taught class. And I said, but you know what? Is your class of comrades here better? And he said, oh, by far, this class was so much better as far as our lesson went. And maybe, Max, you were just telling me that because you felt the need to make me feel good on this 8th day of the 2018 year. But in any case, I appreciated that feedback, which just goes to show you that boys and girls, when you take multivariable next year in college, which is the natural next course that you should take, you will likely find that the first third or so will be a very comfortable breeze. And that's not too shabby to say. I mean, to walk around as a freshman on a university campus saying, oh, I'm in multivariable calculus, it's my easy course. I think if you are having trouble getting into any kind of a party, and if you said that immediately, people around you would be very, very impressed and invite you in no matter what. So in addition to giving you some social capital, I hope that I have helped enlighten you further on the directional derivative and the gradient. And with that, I will say good evening.